I want to give you a couple perspectives on how a conservation of energy problem could be solved using both the law of conservation of energy and using the work energy theorem. So the situation we have is this. There's a girl sitting on a slide, 25 kilograms. At the park, the slide is 2.5 meters high, and she starts at rest at the top of the slide. So she's not taking a running start. At the bottom of the slide, she is on the ground and moving 1.5 meters per second. What was the work done by friction? So in a frictionless world, the girl would have started at the top of the slide, gone down the slide, and at the bottom, the potential energy at the top would have been perfectly transformed into kinetic energy at the bottom. But we're saying here that that didn't happen, that there's friction, and so some energy was lost due to heat. And we're trying to calculate what was that. So the first thing that we're going to do is use the conservation of energy, which is E1 equals E2. The energy at the beginning equals the energy at the end. But we know that it doesn't. So the energy at the beginning equals the energy at the end plus some kind of work. Okay, so some kind of work had to be done by friction in order to make the final energy equal to the initial energy. We've got to account for where that energy went. So there's going to be more energy at the beginning than there was at the end. Okay, so if we do this, then we're going to figure out what that work was. Okay, so the energy at the beginning is going to be equal to the energy at the end plus whatever work was lost along the way. Okay, and so let's put in which energy was there at the beginning, which energy was there at the end. We want to account for where the energy was. So E1, the energy at the beginning was only gravitational potential energy. So that's just EG. There was no kinetic energy at the beginning. At the end, E2, she was on the ground now, so there was no gravitational potential energy anymore. Now there's just kinetic energy, EK. But we also have to account for this work that was done by friction. In order for this side to equal this side, we have to also account for that work. So now, to figure out what work was done, let's rearrange this a little bit. So we get work is equal to EG minus EK. And then when we put in our formulas for those things, we'll be able to solve for this thing. So I'm going to move it over. Work equals MGH minus half MV squared. So our work is going to be 25 kilograms times 9.8 meters per second squared times 2.5 meters. That's the gravitational potential energy, minus half times 25 kilograms times 1.5 meters per second, and that is squared. Now when we do this full calculation, we're going to get the work is equal to 584 joules. Now let's think about what this means, looking back at what we have over here. At the beginning, we had gravitational potential energy. At the end, we had kinetic energy. But it turned out that they weren't the same. In order to make our final energy equal to our initial energy, we had to take our kinetic energy and add that friction work that was done, which was 584 joules. So it turns out that the work that was done was negative 584 joules. We lost 584 joules of energy along the way. The gravitational potential energy at the beginning was greater than the kinetic energy at the end, and so that 584 joules that was there at the beginning, that wasn't there at the end, means it was lost. Okay, so our final answer here is going to be work equals negative 584 joules. Now we can look at this a second way using the work-energy theorem. So the work-energy theorem looks like this. Work is equal to change in kinetic energy plus change in potential energy. Now in our case we're just working with gravitational potential energy, and so that's all that we need. And so then when we expand this, we get work is equal to EK2 minus EK1, that's change in kinetic energy, plus EG2 minus EG1. Okay? Now, some of these things are zero, right? The kinetic energy at the beginning, that wasn't there. The girl was sitting at the top of the slide doing nothing. And so this is just 0 joules. That's a J. And EG2, this is also 0 joules, because at the bottom of the slide, the girl had no height anymore, and so her gravitational potential energy was nothing. And so now when we rewrite this formula, we get work equals the kinetic energy at the end minus the gravitational potential energy at the beginning. And so if we think about this, what we're really looking for how much work was done was what's the difference between the energy we had at the beginning and the energy we had at the end. Whatever that difference is, that's how much energy, that's how much was the change, right? And so we took the final energy, total final energy, minus the total initial energy, and that gives us the change in energy, or the work. So the work is going to be negative 584 joules.